welcome to Step 1, Level 7 of the Colorado Space Grant Consortium's Robotics Challenge, which is driving with an infrared sensor. All right, so far what we've done is we've built a basic chassis, worked with it to control it with an Arduino so we understand how to program it to do basic driving maneuvers. So what we're going to do in this module is we're going to add an infrared sensor that will allow the robot to hopefully detect and avoid obstacles, right? So far, the robot doesn't have any way to sense its environment as we've built it so far. So what we're going to do in this module is we're going to look at how the infrared sensor operates. I'll show you how I mounted my infrared sensor on my chassis. You can do it differently, but I'll show you what I did because we need to mount the sensor to the robot. Go through the basic testing code that we provide to make sure that the sensor is working all right and make sure we understand its operation by actually running it a little bit. Then we'll look at the basic driving code that we use with the infrared sensor. And then finally, your part of the challenge is to use that existing code to program your robot to try to not only detect but avoid obstacles in its way. All right. So the infrared sensor we use, and there's different models of these, so you can look around on SparkFun or other places and find that there's somewhat different models of these. But the basic model we use is by Sharp Electronics, and I won't read it out, but there's its model number. And you can Google it if you like. And the basic way that the sensor works is pretty straightforward, actually. It has two little eyes on the sensor when you look at it. One is an emitter eye. From that eye, it emits infrared radiation or infrared light. That light spreads out from the emitter. If it strikes something that is reflective in the infrared, some of that infrared energy bounces back to the sensor, and it gets detected with the other eye, which we call the receiver eye. Right. So the idea is the strength of the detected reflection in the receiver depends on how far you are from the object. So the idea is we can use the strength of the signal we see in the sensor to try to figure out, is there something in front of us, and give us an idea of how far away it is. Okay, so how does the sensor hook up, right? We'll look at more at the detail of this, but the idea is that the sensor on the bottom, right, so here on the left, has a little plug-in tab, and it takes three wires, a power wire, a ground wire, and then a serial output wire, right? So the sensor is a serial analog sensor, and that's actually very similar to what we used in the Sensors 1 workshop when we started working with Arduinos. So let's see, I'll click on here and hopefully it goes to the right place. Right, so anyway, we won't play the video, but if you need a refresher, just go ahead and follow that link in the slides, and that takes you to the that tutorial that we've already done. Okay, so the idea is there's the sensor eye that we're going to hook in a few minutes. I'll show you how to hook in. And in order to hook it in, we need a little wiring harness, basically, that you can buy that goes, right? So it has a little tab at the one end that plugs into the tab on the bottom of the sensor eye. And it's wired again with three wires, red for power, black for ground, and yellow for the signal. Okay, so when you get if you have a new unused wiring harness, first thing you're gonna need to do is strip a little bit of the wire off the bottom of the harness. So using your wire stripper, I suggest maybe around 1/4 of an inch or something. You don't need to measure it, but you can kind of eyeball it. Right, so the idea is strip each of those wires down about 1/4 of an inch. Now we're gonna need to plug those into our Arduino. And these wires, you'll notice, are stranded wires, so they've got a number of different strands. So in order to keep them from kind of fraying and things like that and make it easier to plug in, for at least for now, what we suggest, or what I suggest, is just twist those those strands together a little bit so that they got a little bit of twist in them. That'll make them easier to plug in. Okay, so so then what you should do is connect the wiring harness to the IR sensor. Notice that it basically is keyed in the sense that there's a little tab on one side and not the other, so you can only plug it in one way. So if you're trying to plug in and it doesn't seem to want to go, you probably just need to flip it over and don't force it, but you ought to feel it slide and click in when you plug it in. Right, and there's a picture of it showing the way it goes, what it looks like when it's plugged in. Okay, so then we need to connect the wires to our Arduino board, and remember, we're not going to connect directly into the Arduino because we have our motor shield, which is mounted on top of our Arduino. But the thing about those stackable header pins on the motor shield is they're designed to allow us access to whatever pins are below them, right? So the idea is if you plug into the stackable header on the motor driver, it actually is connecting down to the pins below, whatever pin is directly below it on the Arduino. So what we want to do, again, remember, red is power, black is ground, and yellow is signal. So you want to plug the red wire into the stackable header that goes down into the 5-volt power below on the Arduino. The black needs to get plugged into one of the two grounds down there below. And then finally, we're going to use pin A0 as our input pin from our sensor. So go ahead and plug the yellow wire into A0. All right, let's take a look at the signals we are going to expect to get out of the IR sensor and how we can use that to use the infrared sensor as a proximity sensor for obstacles. So on the right hand here is a graph of how a typical response for the infrared sensor if there's something reflective in front of it. Right, so on the right side, on the bottom here is graphed the distance to the object. So on the right side, we're further from the object. At the left side, at 0, we're basically right in front of the object. And then on the vertical axis is the voltage that the sensor will put out depending on distance. Right, so what we can see is that if we started out pretty far away, right, so 80 centimeters is about about 3 feet, not quite 3 feet, from the sensor with say a sheet of paper or something, or an obstacle, we expect a pretty low voltage, right? Here, at least according to this graph, we're maybe at 0.4 volts or something like that. And then as we move closer to the object, or we move the object closer to the sensor closer to the object, we expect that the voltage to rise. At first it rises pretty slowly, and then when we start getting pretty close, it really starts going up. So that by the time we hit about 5 centimeters, which is about 2 inches, right? So pretty close. It turns out we expect that the voltage of the sensor is going to peak at maybe just over 3 volts or something like that. And then as actually we move the object closer to the sensor, it turns out that the voltage is going to drop again. And this is actually going to be important for how we program it. The reason that happens is that as we get closer and closer to the sensor, it basically sees a smaller and smaller spot of the reflective material, so it looks less bright to it actually. If we get our object too close to the sensor, in fact, we could potentially see a voltage that's lower than if it were far away. So the idea I think you can see here is if we had a robot where we check the sensor, the voltage is relatively low, we can say, okay, we're not seeing an object very close to us. So the idea is we could drive some, check the voltage again, and so on, and then put some sort of threshold in our code that says if the voltage goes above this level, there must be something in front of us, and we could even try to estimate it if we really wanted to, the distance to the object, so that I shouldn't just continue driving forward because I'm going to run into something soon. And I wanted to point out one thing about this graph. It comes off of the data sheet for the sensor we're using, and I don't think we've talked about, or I I haven't talked about data sheets yet, but that's actually a pretty important thing as you're getting ready to go into step 2, where you're going to start choosing, for example, sensors for your robot. At least that's one of the things you could do. Is how do you get information about how the sensor behaves, how to program it, and things like that? Well, if you go to places like SparkFun or Adafruit online, they will have they have lots of different sensors available. And they'll have a page for each sensor, and so they will give a description of the sensor. Maybe they'll usually have example code of using the sensor, maybe show examples of using the sensor, and so on. But one of the things they'll often also post on those pages is from the manufacturer data sheet, right? So I'm going to go ahead and click on this link here, and this will take us to the data sheet for this sensor. Right. Well, it takes us to the page for the sensor. So, right. So here's the SparkFun page for that particular sensor. It gives a description. Over here's a tab with documents. And notice it's got 2 tabs. There's some example code, which we won't look at, but there's also the data sheet, and I am going to look at the data sheet. So here's the data sheet. Depending on the sensor and the manufacturer, the data sheets can be just as short as a couple pages or as long as 30 or 40 pages. And it depends on how complicated the sensor is, what different modes of operation it has, and honestly, it depends on the manufacturer. Some of them are better about writing data sheets than others. So if you look on here, it talks a little bit about the sensor, possible uses for the sensor, operational ranges for the sensor, so on. And if we scroll down, it has tables of those things. It has actually internal block diagrams of how the sensor works internally, which we don't need to know, but if you're interested, you could check out. Other things that you might need to know if you were starting from scratch for the sensor. We aren't. We have some background material. But eventually, if you scroll down, you find that graph that we were looking at, right? So one of the things that is really, I urge you to do is, if you're looking at sensors, or if you've bought a sensor, that you go ahead and take a look at the data sheet, among other things, because you can often learn interesting things about how the sensor works and things that'll be useful for you in using the sensor. And notice often it's useful to do that even before you purchase the sensor, so you can make decisions about, does this sensor really meet my needs or not? All right, now let's talk a little bit about mounting the sensor to your robot or your chassis. Of course, it depends on the chassis you have and things. But if you're working with the standard chassis that I'm working with, the one we recommend for step 1 of the challenge, it's a pretty small chassis, as we've noted. It does have a few attachment points on it, but not a lot. Some bigger, more expensive chassis will have a lot of attachment points for things. So if you're upgrading, you can. That's one of the things you get with a more expensive chassis. So what I decided to do for my chassis, and I'll walk you through it here in a minute, is to basically construct or cut down a box that I could attach to the chassis, that I could use to attach the IR sensors to, and also I actually use it to hold, I'll show you a picture here, to hold my battery pack and my breadboard, so that they're not sliding around as much as they were earlier, right? So what I did is I got I just looked around what we had in the house, So I found a box of macaroni and cheese. So we had a macaroni and cheese for dinner, and then I salvaged the box, cut it down a little bit, and basically using just a pair of scissors, a little bit of duct tape to about the size that I wanted, that would fit on the top of the chassis. And then what I did is poked a couple holes in it and used just a couple little pieces of hookup wire to wire the IR sensor head through its connection holes onto the box, like you see here. Then what I did is I poked a couple holes in the bottom to match holes in the chassis and used a couple other pieces of hookup wire just to attach. It's not really tightly attached, but to attach the box to the chassis so it doesn't go sliding around. So anyway, what does that do for me? It gives me that attachment point for my IR sensor, and here's a picture with everything put together. But it also, like I was mentioning, it's a place where I can put my battery pack and my breadboard, where I've got things what I'm using as my sort of wiring board to connect things together. And so that way, when I'm working, they'll slide around. Those pieces will slide around a little in the box, but they won't slide off the chassis anymore like they were earlier. So I've added a little bit of structure, and it does a couple things. It holds some stuff, but the main reason I added it was a good attachment point, so I could hook my IR sensor to it. Okay, so once you have your IR sensor all connected and attached to your robot, you can test without attaching to your robot if you like, but I went ahead and attached it and then started doing my testing. We provide a piece of code called testing IR sensor, so we provide this sketch, and what that sketch is a relatively basic sketch just to look at the output of the sensor and make sure that it seems to be working all right and we understand the output that the sensor is giving us. Okay, so we'll just take a quick look through the code. We assigned we plugged the IR sensor into the A0 pin, right, the analog 0 input, and so I define that as IR sensor pin, and that so when I need to address that pin, I can just use this variable to address that pin later in the code. And then I created some variables. I actually created more than we need, but I like to fiddle with data and make look at it in different ways. So I created two variables to hold the output value of the infrared sensor, and that's an integer. Remember, from the Sensors 1 module, where we worked with the potentiometer, that the Arduino board has a built-in analog to digital converter, or ADC. It's a 10-bit ADC, which means that an analog pin will return something between 0 to 1023 as an integer, right? Because 1024 is 2 to the 10th power, so that's is just due to the number of bits in the ADC we're using. Of course, what we really want is not that integer value. What we really want is to turn that into a voltage, because then we can use the data sheet to interpret that value. So I created a floating point variable to hold that voltage called IR sensor voltage, and we'll read the pin and then do a calculation to assign a voltage to that variable further down in the code. Then what I did is I wanted to be able to track what was the maximum and minimum value that the sensor had seen since I had turned it on. And so I created two integer variables just to hold those values. So I called them IR max and IR min. And I initialized them in this way, which at first might seem funny, but it makes sense if you think it through. So for example, for the IR max value, I initialized it as the lowest possible value. And why did I did that? Well, once I've read the sensor, if its value is higher than that, I can reassign that value, right? So, and similarly with the minimum. And then finally, I created just a counter variable to count how many times I've looped through a void loop, with the idea of I want to print some stuff I want to print out not every time I loop. So I'm going to use that variable to keep track of how many times I've gone through the loop since the last time I printed stuff out that I want, and some stuff I'm only going to print out every 50th time, not every time. Okay, so right, so we set up in void setup serial output, obviously, and then we sent the IR sensor pin A0 to be an input pin. Then we go into void loop, right? So in void loop, first thing I do is I read what the value of the IR sensor pin is, right? So we just use analog read to read that pin. And then we calculate the voltage, or I calculate the voltage that corresponds to, right? And if you're looking at this calculations and thinking, what is he doing there? Go back to the sensors one module, and Wesley talks you through doing this with a potentiometer. So if this looks unfamiliar, go back and review that material. But basically, this will give what this calculation does is it says if IR sensor value is 0, the voltage is 0. If IR sensor value is its maximum, which is 1023, it's 5 volts, and then it's somewhere in between probably. So every time through void loop, I print out what the pin read, so the integer value, and also what the voltage is that corresponds to, right? And then if we come down here to lines 59 through 65, I use some if statements to check whether the value we're seeing is larger than what we stored as our current maximum value or smaller than what we stored as our current minimum value. The idea being, if I'm seeing a new higher maximum value than I've ever seen before, I want to assign that to IR max. And similarly, if I'm seeing a lower value than I've ever seen before on the sensor, I assign that value to IR min, right? So the idea is, as the thing is running, it will just keep track of what's the highest and lowest values I have seen on the sensor since startup. Right? Okay. And so then, as I mentioned, those values I print out, but I don't print them every time. I only print them every 50th time. So that what I do is I use it. There's various ways I could do this, but the way I chose to do it is using my counting variable, right? So I initialized as 0, so the first time I go through, I increment it by 1, it becomes 1. I then check and see, am I up to 50 yet, right? And of course, the first time through the answer is no, so I don't enter this if. But eventually, after I've incremented I 50 times, I will hit the point where I is equal to 50, and then I do enter the if statement, and there I do some fancy, I put some asterisks up, but also then I print what's the maximum IR value and the minimum IR value, and just in terms of, again, that integer value. And then I also compute the voltage that corresponds to and print that out as well. So that every once in a while on my serial monitor, I get a printout of what's the lowest and highest values I have seen since I started things. Okay. And then the final thing I have to do in here is, if I don't reset my counter, it's going to keep counting up and it's never going to be equal to 50 again. That's not quite true, but it will be a long time before it's equal to 50 again. So the last thing I do in my if statement is I reset my counter to 0 and I start counting over again. All right, so I've got my robot set up on its stand. It's actually right now running the IR test code. So we won't try to read. I'll do a screen snap later, but you can see it's collecting values. And you can do this a lot of different ways. You can just use your hand or something like this. But one of the things I tend to do is use a sheet of paper as my test object, move it in, move it back out again, right? And then take a look at the output to see that things are working all right with my IR sensor, and we'll do a screen snap showing the results of that. Okay, so let's take a look at the output from the test IR sensor code. So it's actually running on the robot already, but I'm going to refresh it by re-uploading it so it starts with fresh values. Okay, so I've uploaded it. Pop open the serial monitor. I'm going to stop auto scrolling and scroll back here a little bit. So you can see right now it's reading very close to 0 volts, right? Just above 0 volts, because there's nothing in its field of view right now, right? So the max it's seen since I started it, now 10 or 20 seconds ago is basically 0.05 volts. That is, it only returned a value of 11, and 0, it's gone as low as 0, which is fine, right? That's what we expect. Okay, so now I'm gonna test the sensor by using my piece of paper. You can't see it, but I'm moving this piece of sensor paper slowly and closer. I'm gonna stop scrolling here. Look back. So you can see the voltage went up, right? Depending where I had the piece of paper, it was up around 1.2, something like that. And I hadn't gotten real close, so I got up to about 1.3 volts. And you can hear the dogs having having a fight over a toy in the background. So the joys of working from home. So I'm going to scroll again here, and I'm going to see if I can get a higher value. All right, so I got the piece of paper pretty close to the sensor, actually closer than 5 centimeters. And you could see that in my particular case, it didn't quite get up to the 3.2 volts or whatever the data sheet, the graph on the data sheet said. It got up just under 3 volts. So your mileage may vary depending on a lot of things, your sensor, exactly what you're using to do the reflecting and things like that. But anyway, from this, I can see that my sensor is working just fine. So now I can actually start to try driving with it and detecting obstacles with the robot driving. So once you have attached and tested your IR sensor to make sure it's working, you can try and drive with the IR sensor. And we provide a very basic driving code that uses the IR sensor to sense what's in front of it, called Driving with IR Sensor. We'll take a look through the code. What you'll notice, or hopefully you'll notice, is there is some new code in here, but a lot of the code in the in this code is actually taken from the advanced driving code as well as the testing the IR sensor code, right? So basically, I cannibalized earlier pieces of code to build this code, which is a good, I think is a good habit. Never write new code when you can use old code or modify some old code that you have. Okay, so what's in the code? Well, we set up the driving pins just like in the advanced driving code. I set a variable called time default, which I think is in that code as well. And that's what I'm going to use to control how long the robot drives in between checks on the IR sensor, right? Because the robot does things, or the Arduino does things fast, but it only does one thing at a time. So the idea is you need to drive a bit, then check the sensor, then drive a bit, then check the sensor, and so on. So I set as a default 500 milliseconds, so half a second. That it turns out that value and some of the other values in here are you're probably going to want to change, and we'll see why. But basically, they may not work well for your robot. So one of the things you'll need to do is is do a little bit of testing to see what values seem to work well for your robot, so that allow it to detect obstacles in front of it and not run into them. Then we have some variables that are from the IR sensor code, right? So setting what the pin we're using, and again, the values where we read in the sensor value and calculate a voltage from it. I've added another variable called object detected. And the default for that one is 1.0 volts. The idea is this is what we're going to use to compare to our IR sensor voltage. And the idea is if the IR sensor voltage is above this value, it indicates that there's something in front of the sensor, and we're not going to want to drive. If it's below that, we're going to assume that we're not seeing an object in front of us, and it's safe to drive. Okay, so void setup, doing the normal void setup thing, set up all our pins and our serial output, set a delay of 20 seconds before things start to run. Then in void loop, we read the sensor value, calculate a voltage from it, and then I use an if-else statement to decide whether it's safe to drive, right? So if the IR sensor voltage is less than what we've set as object detected, we're assuming it's safe to drive. So we print some stuff out to the serial monitor saying we think it's okay to drive and what we measured on the sensor. And then we use the forward function from the advanced driving code to just drive straight forward. If IR sensor is equal to or greater than object detected, then we do the else part of this statement instead. And what we do is say, well, we must be at 1 volt or more, which suggests that there's something in front of us. So I print that information out to the serial monitor, and we use the stop function to say we're not going to drive in this time interval. We're just going to sit here and see what happens. And notice that actually is the end of the code, and there's a bunch. The functions from the advanced driving code are further down in the sketch. But notice this is a very simple code, right? So the idea is the robot's going to drive until it sees something in front of us. Then it's not going to try to avoid it. It's just going to stop. And unless we come in and move the object or move the robot, it's just going to sit there, because every time it checks now, it should see that the object is still in front of it and decide that it shouldn't drive. What we're going to do is go ahead, you should do is test with this and do some testing to determine how well these default values up near the top are working for you. The ones I'm going to work with as I am adjusting things, I'm going to probably lower the motor power. So I'm going to change PW straight A and PW straight B, right, in lines 26 and 27 to be something less. I've done this already, so I kind of have an idea of what's going on. I'm going to need to lower the default time because 500 milliseconds turns out for me to be too long, or for my robot, and it drives too far. So something that's not anywhere close to it, it'll drive for a half a second and hit, and then of course it won't realize it's hit it because it's now closer to it and the sensor is going to be reading low. And the other thing that I have played around with adjusting is my threshold here, my object detected, so that you might want to do that as well, adjusting it up or down depending on how sensitive your sensor is and what other things you're having with your robot. And notice the thing that is fun but makes it a little more complicated here is that there's an interplay between those four variables, right? Three: the speed of the robot, how long we drive, and what our threshold is. If I raise the threshold, that affects the default driving time potentially. That is. I can get the same results with my robot by adjusting to different combinations of these variables. Again, what I suggest is do a little bit of testing with the robot on the floor and see which values work for you. So you can see in the video that that's my robot just driving with the defaults, and with the defaults for my robot, it doesn't see the object right, in the sense it drives too long, right? 500 milliseconds is too long, and so it's far enough away from the object that it doesn't detect it. So it decides it's okay to drive. By the time it has checks again, it is actually hit my shoebox, right? Is my little object. And in that case, sometimes it will actually push the box. In that particular case, it kind of bounced off, and I think the box got just far enough away that then it could detect it, so it stopped driving. But anyway, you can see that I'm going to need to adjust my values somewhat in the code so that it will drive forward and not hit the object. All right, so now I've made some adjustments to a couple parameters like I'd mentioned before. And now you can see that when the robot drives, it gets close to but doesn't actually hit the object. And so notice it just sits there. If I move the box, then it thinks it realizes it's clear again and drives forward. So that's what you ought to try to get to, and you just kind of play. You ought to play with it, and again, take the time you want. There's not a you can spend a lot of time exploring different combinations of parameters if you like, but at least getting an idea of what works as an okay default for your robot to drive. So that took me. I had to try 2 or 3 times before I was happy with it. So I could get it driving like that. Okay, so the final test, or the thing you need to do to advance to step 2, so complete level 7, is now try to modify things a little bit in that driving code. And what I suggest normally is, what I do is I make a different copy of the code with some other name so I can work on it and still have my default code around if I need it. But the idea here is what you want to do is not just, right, you notice it's not horribly effective for the robot to just drive, detect an obstacle, and say, well, I'm going to stop until the obstacle goes away, because it's probably not, right? So the next level of functionality we want to add is, okay, let's add some code and see if we can figure out some code that will cause our robot to, when it detects something in front of it, tries to avoid it. So what I'm going to do is I'm going to add some code. I'm going to work on the code and try to just have my robot detect what's in front of it, then see if I can't get it to turn and drive around it. And I would suggest for this part, don't get too fancy to start with, because it turns out we've got the basic building blocks for all the stuff, right? We have the functions we can call and so on, but the code logic actually gets it can get complicated pretty quickly, where when you're trying to code an algorithm where the robot avoids an obstacle, right? You can get kind of stuck in infinite loops. It may not succeed, or and if the code is too complicated, it may be difficult to understand what it's actually going to do. You thought it through, but it turns out it behaves a little differently than you thought, which is, it's part of the fun, and part of the challenge here. But anyway, I'm going to just try to do a relatively simple, see the obstacle, stop, turn a particular direction, see if I think I see a clear path with the robot. If so, drive forward. If not, keep turning a little bit. So we'll see, right? I haven't tried this yet, but I'm gonna try it now, and then I'll show you the results of what I code. Right, so there's my video of my robot doing a very simple avoidance, a type of maneuver with obstacles, and I added, for fun, I added a second box in that it could try to avoid. And again, what I did is super simple. You can definitely do more. When it detects an obstacle, all it does right now is the robot tries to turn left 90 degrees. If it thinks it's clear ahead, at that point it keeps going until it sees something else. Then notice it saw the second box, turned left, and it would have just kept driving around till it got stuck, or avoiding things by turning left. And you can obviously imagine that you might want to do driving that's more complicated, right? But at least that shows that I've got the basics down, and I can code a very simple solution, and then I can, just by adding to it and working on it, I could add more stuff if I wanted. So congratulations. If you've reached this point, you've advanced to step 2 of the Colorado Space Grant Robotics Challenge. So what's next? Well, step 2 is where you add additional capabilities to your robot. And those capabilities could be more advanced code, physical enhancements, like if you didn't like the way your robot drove in terms of the traction it had with the ground or something, you could try and modify it that way. Obviously, you could add additional sensors, or a display, other things. You kind of, the world is opened up now, right? You have a basic functioning robot. You have an understanding of how to use the Arduino to program your robot, how to interface the Arduino with the robot, and the Arduino with sensors, and use the input from the sensors to make the robot do things. So there's plenty more to learn, plenty more to do, but you have the basics under your belt right now. What I suggest doing is, if you're thinking of going on into step 2 and then ultimately into step 3, is look ahead at step 3. What are the challenges that we outline in step 3? And they're pretty broad brush, and you have a chance to define creating a more defined challenge based on the very broad challenges in step 3. Things like swarm robots, or better navigation, or things like that. But the reason I suggest that is, if you know what you want to try to do in step 3, that will usually help you choose how to enhance your robot in step 2. So even though there is this sequence of things you need to do, knowing ultimately where you want to go will affect how you want to modify your robot, or the ways that you want to modify your robot. So anyway, again, congratulations. You've completed the first step of the Colorado Space Grant Robotics Challenge. You've created a very basic functioning robot, and now hopefully you will have a lot of fun and challenge yourself to do a lot more difficult and more interesting things with that robot.